In this video, we're going to go through a worked example to find all the points where a graph is increasing, decreasing, concave up, and concave down by hand. So let's jump in. Okay, so here's the problem. Go ahead and pause the video and see if you can work this out on paper. This one's a little trickier, just FYI. Cool. Okay, so here's the answer. If you got this, then feel free to skip this video. Otherwise, let's dive into exactly how we got it. So first off, let's find the critical points for this function. That's what they're asking for, critical numbers or critical points. Now, I've already created another video on critical points, so I won't go over, why they make sense or what they're used for, but basically I'll just apply that here. So the critical point, by definition, is any point on the function, so any point that's in the domain of the original function, where the derivative is equal to 0 or does not exist. So let's think about that. In order to find those critical points, we first need to take the derivative. So that's always step one when you're finding critical points. So let's actually do that. Now, how do we take the derivative of this thing? How do we take g prime? Well, here, hopefully it's clear that we would use the quotient rule because we have a quotient of two functions, x squared plus 9 and 2x minus 3. So if we actually take the quotient rule, I won't go through the quotient rule either. I have a separate video on that you can check out. But basically what you do is you take the derivative of the numerator, which in this case is 2x, times the denominator, not the derivative of the denominator, just the denominator itself. And then you subtract the numerator, x squared plus 9, and then multiply by the derivative of the denominator, which in this case is 2. And then you divide by the denominator squared. So in this case, 2x minus 3, the whole thing squared. So there you go. That's the derivative. Now, even though this is true, we probably want to simplify it down a bunch. So let's do that now. What's something we can do? The first thing we can do is distribute 2x into here. So what would that be? That would be 4x squared minus 6x. Hopefully that makes sense. And then the next thing we can do is we can distribute this 2 in here, and we can also kind of distribute the negative sign in if you want to think of it like that. So if we do those, hopefully it's clear that that would be negative 2x squared minus 9 times 2, which is 18. And then we're still all over 2x minus 3, the whole thing squared. If we simplify it a little further, we can combine like terms. So let's combine all the x squared. So 4x squared minus 2x squared, that's 2x squared minus 6x minus 18 all over 2x minus 3 squared. So we have that, and then I see actually another simplification we can make. We can actually factor 2, it looks like, out of the numerator. So if I do that, I'll end up with 2x squared minus 3x minus 9. So 2 times all of that, all over 2x minus 3, the whole thing squared. So there you go. Here's the derivative. So we've taken the derivative. Now remember, for the critical point, we need to find any x values that cause the derivative to equal 0 or just plain not exist. Let's start off with getting a derivative of 0. Hopefully it makes sense that in order to make the left side equal 0, basically what that comes down to is making the numerator equal 0. If we can make this numerator equal 0, or if we can find the x values that do that, those will be the x values that make the whole derivative 0. Because if the numerator is 0, you're just multiplying by 0, which is 0. So how do we do that? Here, and by the way, we don't really need to worry about the 2. What we really need to do is make this thing 0, because if we can get 0 times 2, that'll still be 0. So we're really trying to solve this equation, if you think about it, the simplified equation. X squared minus 3x minus 9 equals 0. If we can find the x values that do that, those will be the x values that make this whole derivative 0, and those will therefore be critical points. So how do we do that? Usually when we deal with quadratics, so this is a quadratic equation, usually we solve these with guessing and checking. And we want two numbers that we can multiply to 9 or negative 9 and add or subtract to negative 3. So think about all the factors of 9. You can always start with like 1 and 9. Those obviously multiply to 9. We'll deal with the positives and negatives later. But here, these two would work. The problem is if I add or subtract them, if I add them, I get 10. If I subtract them, I get 8. Neither of those is 3. So that won't work. Actually, do this in a different color. So these won't work. The next thing to try would be 2, but the problem is that 9 is not divisible by 2, at least as a whole number. Like 4.5 would work, but we generally just look for whole numbers when we're guessing and checking. The next thing we could try is 3 and then 3. That multiplies to 9, but if we add those, that would equal 6, which we don't have, and if we subtract them, that would equal 0, so that also wouldn't work. And after these two numbers cross, like if we go up to the next one, like 4 would not work, 5 would not work, 6 would not work, 7 would not work, 8 would not work, 9 would work, but we've already taken that into account. So as soon as the first number equals the second number, you've already exhausted all your possibilities for guessing and checking, at least with whole numbers. So basically, guessing with whole numbers fails here. Now again, that doesn't mean there's no answer here. It just means we have to rely on a separate method. So what's our separate backup plan to find or to solve quadratic equations? Basically, the quadratic formula. Remember, what does the quadratic formula say? It says if you have a quadratic given by a times x squared plus b times x plus c equals 0, if you start off with something like this, basically the solution would be x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And hopefully it makes sense that in our case, a, the coefficient on the x squared term would be 1. If it's not written, you can assume it's 1 because 1 times anything is itself. And then b would be negative 3 here. And then c would be negative 9. So if we pop those in, think about what we get x equals negative, and then b is negative 3, plus or minus the square root of negative 3 squared minus 4 times 1, and then times c, which is in this case negative 9, and then all over 2 times a. So a is 1. So there we go. Now we can kind of simplify this down a little bit more to see what we get. So we get x equals positive 3 plus or minus the square root of 9, and then minus 4 times 9, that'll be 36. So that'll be plus 36. Yeah, plus 36. And then all over 2. Then we can simplify further. So what is 9 plus 36? Hopefully it makes sense that that is 45. So we'll get 3 plus or minus the square root of 45 all over 2. So that's good, but we can simplify even further, actually. If you notice that we can further simplify 45, if you start off with 45 and we try to basically do what's called the prime factorization, hopefully it makes sense that you can break it apart into factors 9 and 5. 9 is not prime, 5 is prime, so we can circle that. 9 can be broken down into 3 and 3, both of which are prime. So the prime factorization here is 3 squared times 5, which means if we try to take the square root of everything, like you can think of here, if we try to take the square root of this, you can think of the square root of 45 as being equal to the square root of 3 squared times 5. So what we can basically do, the square and the square root, at least on the 3, because we have 2 of them, are going to cancel out, and you can effectively pull a 3 onto the outside. Again, that's kind of an algebra topic. I won't go into too much detail on that, but basically what I'm saying is you can factor out, you can simplify it like this. So hopefully that makes sense. And by the way, if you're skeptical of that, plug this into your calculator and this into your calculator and verify that they're the same number, just as a decimal. Cool. So that's good. And now, again, as we keep making progress, they've already set up this problem. By the way, this is a non-calculator problem. If we had a calculator, this would have been a lot easier. We could just graph it and look. But you can solve this whole problem without a calculator. The big reason that you can solve it without a calculator is because they have set up the problem in such a way that as we keep moving forward, there are going to be clearer and clearer simplifications that we can make. So like here, after we simplify that, hopefully it's now clear that we can factor out a 3. And actually we can factor out a 3 halves to make it really easy. So 3 halves plus or times 1 plus or minus the square root of 5. And remember, this is really 2 separate numbers. This is really saying x equals, I'll say 3 halves times 1 minus square root of 5. Again, this is just some number. Even if it's an ugly number, it's just some number. and then 3 halves times 1 plus square root of 5. So here are two solutions. Now remember, what did we just do? We just did a lot of algebra, so it can be very easy to get lost in what we did. But basically, what we found all the spots that make the derivative equal to 0. So we found all the spots that make the derivative. So these are the two x values. Long story short, that make the numerator equal to 0, which would make the derivative equal to 0 at that spot. So if I copy this down, you can see that those are the spots that would make the derivative 0. But remember, that's not all that we need. We also, because the definition of the critical point is any x value that would make the first derivative 0 or not exist. That or not exist part is actually important. So hopefully it makes sense. If this is the derivative, what x value would make this not exist? Hopefully it's clear that when the denominator is 0, basically 2x minus 3 would equal 0. If you set that equal to 0, you would get x equals 3 halves. So 3 halves is the value that makes the first derivative not exist. So hopefully that makes sense. Now there's even an extra layer of complexity here that has to do with the nuance of the definitions. So let me just kind of refresh. The official definition of a critical point or a critical number is any x value that is within the domain of the original function where the first derivative is 0 or does not exist. That in the original domain of the original function is an important piece of it. Remember what the original function was here. The original function, if I go back up to the top, was this. So if I come down here now, this was the original function. So even though there's no problem with the first two, but even though for this one, x equals 3 halves, it's true that that does make the first derivative not exist. However, this point is not even in the domain of the original function. So even though it makes the first derivative not exist, this one can't be a critical point. Now, that might seem kind of weird, but why does that make sense? Basically, think about it like this. Critical points are essentially potential relative extremes, potential relative maxes, or potential relative mins. So doesn't it make sense that in order to be a relative max or a relative min, basically think about the definitions of those first. What is a relative max? The definition of a relative maximum is a point where the y value is higher than all of the values right next to it. And a relative min is basically the same definition, it's just less than. So the definition of a relative min, and again, you can kind of think about this, a relative max would be a point that has a higher y value than all the spots right next to it. That's what makes it a relative max. A relative min is a point that has a y value that's less than all the y values right next to it. So doesn't it make sense that if the function isn't even defined there, so pretend we have a hole rather than like kind of a filled in slot. So if we don't even have, if the function isn't even defined there, if we have a hole or an asymptote or whatever, doesn't it make sense that it's not possible for it to be a relative max or a relative min? Because in order for it to be a relative max or min, it has to be defined there to begin with. So hopefully that makes sense about why we have to exclude those points when we're looking for the critical points. But yeah, that is an important detail to keep in mind. So hopefully that makes sense. Okay, so now let's work on part B. In part B, they're asking us to find the intervals where the function is increasing. So let's think about this logic. What does increasing mean for a function? Basically, it means that the first derivative is positive, because the first derivative tells you the slope. If the slope is positive, that means you're going up, you're increasing. If the slope is negative, that means you're going down, you're decreasing. So what we're trying to do is find the x values where the first derivative is positive, basically. Now, the problem is there are an infinite number of values, and we don't really want to go through all of them. So we need some other way to choose our values. And the best way to choose the values is to think about all of the points where we could turn around. If we're going, up and down, think of all the points where we could change slope or change whether we're increasing or decreasing, and just check those and then check certain sample points. So that's what we want to do. Now, where are the points that we can turn around? Basically, those are the critical points from the first problem, with one small caveat. And this is kind of a weird detail, so hopefully this makes sense. Now remember, on part A, we had to exclude x equals 3 halves because the original function, it turns out, is not defined at x equals 3 halves. Now, even though the original function isn't, so if we were looking for relative maxes or minimums, then we should delete that from the list of critical points. However, if we're trying to look for the points where either the function changes from increasing to decreasing or it changes concavity, we actually do not want to get rid of that point. Here's why. Think about the function 1 over x squared. So here, this is roughly the graph of y equals 1 over x squared. That's not what we're dealing with here, but just pretend. Do you agree that the function is definitely not defined at x equals 0 in this case? We have a vertical asymptote there. But just because the function is not defined there doesn't stop us from changing the slope across that point. So to the left of it, hopefully it's clear that all these values really are positive to the left, and to the right of it, the values of all the slopes really are negative. So even though the function doesn't exist there, the original function, it can still change from increasing to decreasing. So that's kind of a weird idea, but that's important. Basically, what that means is that we need to include all the things we would have included from the critical points without taking them out just because they were not in the domain of the original function. So in other words, we should look at x equals 3 halves here as well, I guess is what I'm saying. So there you go. These 3 points, hopefully it makes sense, because they're critical points, or kind of a slightly different version of the critical point. These are the only points where the function can turn around, basically, change from increasing to decreasing or vice versa. So how do we tell which one is which? Basically, we do this with a sign chart. So here, let's think about our sign chart here. Remember, the whole point of a sign chart is we're basically checking the signs of the first derivative, or you could do, maybe the second derivative, depending on the question. But that's kind of the idea. So first, we need to choose our x values, and then we can take the first derivative here. So with these, hopefully it makes sense. And again, this is a non-calculated problem. So they want you to solve this purely by hand. And the fact that they want you to solve it purely by hand, in order to do that, I should say, certain things need to work out. And they need to choose the problem so that they work out. So in this problem specifically, you can see that we're able to factor this as 3 halves times 1 minus square root of 5 and 1 plus square root of 5. And also this one's 3 halves. So with sheer logic, you can hopefully see that 3 halves, and by the way, think about it like this. Think about it like 3 halves times 1 plus square root of 0. You can think of it like that. But 3 halves is going to be between these two. So 3 halves times 1 plus square root of 5. That we know that has to be bigger than 3 halves because square root of 5 is a positive number. So it's like if we didn't have square root of 5 here, clearly that would just be 3 halves. And now we're just adding some positive number. So yeah, that's clearly got to be bigger than 3 halves. So we know that. And then by similar logic, we can figure out that 3 halves times 1 minus square root of 5 has to be less than 3 halves. Again, because if we didn't have the minus square root of 5 here, that would be 3 halves. So 3 halves minus some number has to be less than 3 halves. So we can think through that. And now what we want to do, so these are the only points we know that things can turn around. So this would be like, we don't really care about what the slopes here are, what the slopes are here. We know that the slope here is 0, and here actually does not exist, but that we don't really care about. We just care about that those are spots where the slope could change. So now what we need to do is choose sample points. How do we choose sample points with this problem? It's kind of interesting because basically what we need to do is we need to choose certain values. We need to choose a certain value that's between 3 halves and 3 halves times 1 plus square root of 5, whatever it is. Now these each have ugly decimal expansion. So like, for example, you could choose like 3 halves, we know that is 1.5, right? You know that at least. This thing you don't really know. You know it's bigger than 1.5, but how big is it? You don't really know. So you could just try to choose 2 and cross your fingers and hope that that is less than this thing. We know it's definitely bigger than 1.5, but we're pretty sure, but we're not certain that it's less than this. So you could do that. And on the other end, you could choose 1 because we know that's less than 1.5. But again, that might not be the best thing to do because you're never really going to be sure. Yeah, you're never really going to be sure unless you think about it a little bit differently. So the best way to think about this is actually to, again, instead of thinking about 3 halves, think of it as if it's written like this. In other words, write it in the same format as the other things. So, and then here's the trick. Basically, we know that this is 0, and we know that that's 5. So if you just choose a number between 0 and 5 and plug it into this format, that will give you a number that's guaranteed to be between them. So how would you do that? What's the easiest number we can choose? Probably 1, I would say. So hopefully it makes sense that this will be 3 halves, 1 plus square root of 1. And that is guaranteed to be between this and this because 1 is between 0 and 5. And otherwise, it's the same format. And then now if you solve this, what's 1 plus square root of 1? That's 1 plus 1, which is 2. And then 2 divided by 2, well, that's just 1. So hopefully it makes sense that this whole thing simplifies to 3. And then you can do something similar with the other ones. So here, this would be like subtracting 5. So you can kind of write this as 1 minus square root of 0. Again, as long as you choose a number between 0 and 5, they'll be subtracted, and you'll be guaranteed that they're bigger. What's the easiest one you could pick? Here I would say probably 1, again. So think about this as like 3 halves times 1 minus square root of 1. Well, square root of 1 is 1. 1 minus 1 is 0. So 3 halves times 0, that's just going to be 0. So you're guaranteed that 0 is between those. So hopefully that makes sense. And then one other thing we need to do is we now need to choose values on the outside of here. So the best thing to do is, again, you can do a similar strategy if you want to choose a number that's guaranteed to be greater than this. Basically what we should do is we should choose a value that is bigger than 5 here, but otherwise use the same form. So you could choose like 3 halves times 1 plus square root of 6. That's guaranteed to be bigger. Or square root of 7. That's guaranteed to be bigger. Square root of 8. You could do that, but what you also want to do is you want to minimize your work. So you want to choose a number that's bigger, but also the next perfect square. That's probably the best thing to choose. So I would actually choose 9 here. I would actually call this 3 halves times 1 plus square root of 9. Why? Because square root of 9 is easy to calculate, and it's a clean whole number. So square root of 9 would be 3. 1 plus 3 is 4. 3 halves times 4, that'd be 3 times 2. That'd basically be 6. So just with that logic, we can be sure that 6 is greater than that. And then on this end, we can use similar logic. I'll also use 9. It's just that I'll be subtracting instead of adding. So 3 halves times 1 minus square root of 9. What is that? Square root of 9, remember, is 3. 1 minus 3 is equal to negative 2. 3 times negative 2 divided by 2, that'd be 3 times negative 1, which is just negative 3. So there we go. We can guarantee that these numbers really are sample points, whereas, it probably would have worked out if you didn't do that logic and you just like chose the number slightly bigger, slightly smaller, and then you chose like 10 for each of these or 10 for this and negative 10 for that. It probably would have worked just because you would have left yourself enough room for guessing. But with this method, there's no guessing. So that's the benefit. So there you go. Those are our sample points. And now remember, if the first derivative is positive at one of our sample points, it's positive for all the values in between. If it's negative for one of our sample points, it's negative for all the values in between that and any other spots where it could change signs. Again, I won't go too deep into the why behind that, but that's true. So now the question is, what do we do with that? Basically, what we need to do is plug each of these sample points into the derivative equation and see what we get. Now here, hopefully it makes sense that, and again, we only care about the sign. That's another thing. We don't care what the number is. We just care about the sign of the number. Now here, hopefully it makes sense that 2, that's always going to be 2 no matter what we plug in for x. And also, this whole thing down here is also always going to be positive no matter what we plug in for x, because even if we plugged in an x that made this negative, it's going to get squared afterwards anyway. So what it really comes down to is whether it's positive or negative if we plug it into here. So that's what we really need to think about. So if I plug in negative 3 into here, think about what that would be. That would be positive 9 plus 9. So 9 plus 9 minus 9. So in other words, that would be a positive number. If I plug in 0 here, I would just get negative 9, which is a negative number. If I plug in positive 3 here, think about what I get. I get 9 minus 9 minus 9, negative number. And then if I plug in 6 here, I get 36 minus 18 minus 9. So that's 36 minus 27, which is positive 9. which is positive. So there you go. We just figured out that, again, remember what the original problem was. Find the intervals where the function is increasing. Hopefully it makes sense from here that it'll be from negative infinity up to 3/2 times 1 minus square root of 5. And then it'll be 3/2 times 1 plus square root of 5 to infinity. This is where the function will be increasing. So there you go. That's how we find part B. So here in part C, they want us to find how many inflection points the graph has. So let's get crystal clear on the definition of an inflection point. An inflection point is a point on the original graph where the function changes concavity. What does it mean to change concavity? Again, I have other videos explaining what concavity is and why it makes sense, but basically it means the sign of the second derivative changes. So basically what we can do is, it's kind of like the last problem, it's just we'll be doing it with the second derivative rather than the first derivative. We've already taken the first derivative in the previous parts of the problem, so now let's just take the second derivative. So if I take the second derivative here, think about what this would be. And again, this will be, really, you can think about it as kind of another round of the quotient rule. But if we do this, let's see what we get. So the first thing I'm going to do, actually, I'm going to pause on this a little bit. I'm actually going to, well, never mind. I guess I'll leave it here. So again, with the quotient rule, we take the derivative of the numerator. So what's that going to be? It's going to be times 2. Then it's going to be 2x minus 3. Right? And then times the derivative, or times the denominator, not the derivative of the denominator. So that's that. So that's the derivative of the numerator times the denominator. And then minus the numerator. So 2 times x squared minus 3x minus 9 times the derivative of the denominator. And this is where we might need a little bit more room. So here we need to think through the chain rule. I won't go through the chain rule in depth here, but it's basically going to be 2 times 2x minus 3. Because basically I do the power rule, drop the 2 down out front, subtract by 1, leave the inner function. So 2 times 2x minus 3 to the first power, and then times the derivative inside, which is 2. So hopefully that makes sense. And then we divide by the denominator squared. So it'll be 2x minus 3 squared, the whole thing squared, which according to certain exponent properties, we can just write as to the 4th. So there we go. This doesn't look very fun, but maybe we can simplify it. So let's see. If I simplify this thing down, hopefully it's clear that I'll get 2 times 2x minus 3 cubed. I just multiply those through. And then the real question is what happens over here. So this will be minus 2. I'll distribute it all the way through, but minus 2. Well, actually I can probably simplify like this. I'll say just 2x squared minus 6x minus 18 times 4 times 2x minus 3, and then all over 2x minus 3 to the 4th. The one thing I'm noticing here is that we seem to be able to simplify a lot with these like 2x minus 3s. So one thing I can do here, and again, there's no guarantee, there's no way of knowing what you'll end up with when you get started, but one thing I can do here is I can just factor 2x minus 3 out of the both terms in the numerator, and I can also factor 1 out of the denominator. So if I do that, let me just see what I get. And again, that's just something I'm noticing as I'm going through now, but 2x minus 3, now I'll only have 2 of them left, and then I'll have minus 4 times that, and actually I can, at the same time, I can multiply the 4 in. So kind of doing a few steps at the same time because this is so annoying to work with. That's a problem. So basically, if I distribute that in, hopefully it's clear that I'll get minus 8x squared minus 24x. And then think about what's 18 times 4. Well, 20 times 4 is 80, or negative 80. And then for each one of those, we go up. There's two that we should add basically for each of those. So hopefully it makes sense. 52. And you can also verify that. You can also do, this is just mental math stuff, but 10 times 4 is 40. 8 times 4 is 32. And then 40, this should be 72. I meant to say not 52. So yeah, 72. Whoops. So yeah, so you can think through it a couple different ways, but once we have that, and then down here we'll have, if we factor out a 2x minus 3, we'll have 3 of them left. And then these cancel out. So there you go. This is what we now have in the numerator. Well, this is what we have left in general. And then the question is, can we simplify this further? So let's try it. So at this point, I would say we probably want to, or at least what I'm going to say is I'm going to cross my fingers that we'll have certain terms, certain like terms that cancel out. So that's kind of what I'm hoping for. Let's see if that actually happens. So in the numerator, I'll have 2 times, and then what's 2x minus 3 squared? Well, if I square that, hopefully it makes sense. It'll be 4x squared, 2x times 2x, minus 6x minus 6x, so minus 12x. And this is actually good news. I can already tell that this is going to cancel like I hoped. So minus 12x, because otherwise we would just be left with a very ugly problem. Generally, when you're doing these by hand, that doesn't happen. They usually simplify decently at least. And then here this will be plus 9. Negative 3 times negative 3. Then over here we have minus 8x squared minus 24x minus 72. All over 2x minus 3 cubed. So that's good. And if we keep making progress here, now first off, I'm gonna distribute the 2 through to each term here. And then I'm actually going to distribute the you can imagine that as negative 1. I'll distribute that through. We need to do that to basically drop the parentheses so we can combine like terms. So this will be 8x squared minus 24x plus 18 minus 8x squared plus 24x, negative times negative, plus 72. All over 2x minus 3 cubed. And then here's the good news. 2x or 8x squared, those cancel, 24. So we're left with basically 18 plus 72. Hopefully it makes sense that is just going to be 90. So long story short, the derivative here, or the second derivative I should say, is equal to apparently 90 over 2x minus 3 cubed. And again, we don't have a word for like the critical point for the second derivative, but it's kind of a similar idea. It's basically any point in the domain of the original function, that's an important detail, where the second derivative is equal to 0 or does not exist. There's no way to make this numerator 0 like we did previously, so that doesn't work. The only thing that can make the derivative not exist is x equals 3 halves. The problem is, remember, x equals 3 halves is not in the original function. So there actually aren't any there aren't any second derivative critical points if you want to think of it like that. I just kind of made that up. Critical points always means first derivative. So if there aren't any, then there can't be any points of inflection, is what we just found. So hopefully that makes sense. So there are actually 0 points of inflection. Now, just to be clear, that doesn't mean that it can't change concavity across x equals 3 halves. In fact, looking at this, it actually does, because if we're less than 3 halves, this will be a negative number, because the denominator will be negative, and a negative cubed is negative. But if that's greater than 3 halves, it'll be a positive number. So actually, it will change signs across x equals 3 halves, which is kind of a weird idea. So the concavity will definitely change across x equals 3 halves. It's just that won't count as an inflection point because it's not a point that's on the actual function to begin with. A lot of nuances and corner cases with this problem. It's a good problem. But yeah, so technically there are no inflection points. However, there is a spot. However, we're predicting that the inflection or the concavity does change from negative to positive across x equals 3 halves. So hopefully that makes sense. Okay, so now let's open this up in Desmos and take a look. Here we can see that, yes, actually the function is increasing on the intervals that we predicted from negative infinity up to this point, negative 1.8541, which is this value, and also from positive 4.8541, which is this value, up to infinity. That's when we have a positive slope. Between there, we actually have a negative slope, just like we predicted from our sine chart. We also knew that x, and again, we didn't answer this problem, but from that same sine chart, you could actually conclude that, yeah, this would have to be a relative maximum, because to the left of it, basically this is the logic of the first derivative test. To the left of it, we had a slope of positive, or we had a positive slope. To the right of it, we had a negative slope. So yeah, whenever it goes from positive to 0 to negative, yes, that is a relative max. And similar thing with a relative min over here, but negative 0 to positive. We also determined that at x equals 3 halves, remember that could not be a critical point. So even though, if you think about it, I won't go there. That couldn't have been a critical point because it wasn't in the domain of the original function. It turns out in this case that at x equals 3 halves, we actually just have a vertical asymptote. So that's why. And also for part C, remember what we just found for part C, we determined that there are no inflection points. However, we also predicted that at x equals 3 halves, it does change concavity from negative to positive, if you remember the logic we just went through, even though it couldn't have been an inflection point because it wasn't in the domain of the original function. You see how that exact prediction is happening here. This to the left of x equals 3 halves, remember this is x equals 3 halves, this vertical line right here. To the left of that, it is concave down. To the right of it, it is concave up. So it does change concavity across there. It's just that we can't officially consider it an inflection point because there is no point there. There's no point to begin with. You need a point for it to be an inflection point. So there you go. Hopefully that makes sense. Remember, we didn't need a graphing calculator to figure any of this out. We figured this all out just with sheer logic alone, all by hand. But the graph, you can see the graph kind of supports everything that we were able to understand before even using the graph. So there you go. Hopefully that makes sense. This is a good function behavior problem. If you have any questions, be sure to post them in the comments. Otherwise, I'll catch you next time. See ya.